Arc length. The objective is to find the length of the curve f of x over the interval a comma b. We know how to find the length of the line segment connecting the point x1, y1 to x2, y2. We form a right triangle where this length segment is the hypotenuse of the right triangle. The horizontal distance is delta x. The vertical distance is delta y. By the Pythagorean theorem, the distance d is the square root of the change in x squared plus the change in y squared. If we call x2 minus x1 delta x and y2 minus y1 delta y, then the distance is the square root of delta x squared plus delta y squared. To find the length of the curve f of x over the interval a comma b, we divide the interval a comma b into n intervals. On each of these intervals, we connect the 2 points on the curve, and we use the distance formula to estimate the curve in any interval. The more intervals we use in our estimate, the better the estimate will be. The difference between the length of the curve and the line segment is the error. For example, to find the length connecting pi minus 1 to pi on the curve f, we find the line segment connecting pi minus 1 to pi, whose distance is li, the square root of the change in x delta x squared plus the change in y delta y squared. But the change in y is f of xi minus f of xi minus 1. And so li is the square root of delta x squared plus f of xi minus f of xi minus 1, the quantity squared. We assume that the function f is continuous and differentiable on the closed interval a comma b. Therefore, on each of these interval xi minus 1, xi, the function f is also continuous and differentiable. We then apply the mean value theorem on each of the interval xi minus 1 to xi. The mean value theorem states that if the function f is continuous and differentiable, then there is a number c on the interval such that f prime of c equals f of b minus f of a over b minus a. But we applied the mean value theorem to each of the interval xi minus 1 to xi. And so f prime of c is f of xi minus f of xi minus 1 over xi minus 1. But xi minus 1 is delta x. We rewrite these formulas as f prime of c times delta x equals f of xi minus f of xi minus 1. But this quantity f of xi minus f of xi minus 1 is in the formula li. And so we substitute it in the formula. We end up with li equals the square root of delta xi squared plus f prime of c times delta xi squared. Delta x is delta xi because we use the same with delta x. We factor out the delta xi squared and move it outside of the square root. The result is delta xi times the square root of 1 plus f prime of c squared. The total length is the sum of all of these length segments. The total length is therefore the sum of the square root of 1 plus f prime of c squared times delta x, where c is any number in each of the interval. But we recognize that this is the Riemann sum, so as n go to infinity or delta x go to 0, we obtain the definite integral from a to b. The integrand is the square root of 1 plus f prime of x squared. Delta x becomes dx. We will use this formula to find the length of the curve f of x on the interval a comma b. For example, find the length of the curve y equals 4, the square root of 2 over 3, x to the power 3 half minus 1, on the interval 0, 1. First, to use the formula, we find the derivative of f, which is f prime of x equals 4 root 2 over 3 times 3 over 2 x to the 1/2 minus 0. Simplifying this, we have 2 root 2 x to the 1/2 or 2 root 2x. We then plug this into the arc length formula. In the arc length formula, f prime of x squared is the square root of 2 root 2x, which is 4 times 2x, or 8x. The arc length of the curve between 0 and 1 is therefore the definite integral from 0 to 1, the square root of 1 plus f prime of x squared is 8x dx. We can use substitution to evaluate the definite integral. Let u equals 1 plus 8x, du is 8 dx, dx is therefore du over 8. Also, if x is 0, then u is 1 plus 8 times 0, which is 1. When x is 1, u of 1 is 1 plus 8 times 1, which is 9. And so using substitution, the length is the integral from 1 to 9, u equals 1, u equals 9, the square root of u, du over 8. This integral is now in terms of u, as well as the lower and the upper limit of integration, u equals 1, u equals 9. The antiderivative of u to the 1/2 is u to the 3/2 times 2 over 3. Evaluate from 1 to 9 using the fundamental theorem of calculus. Simplifying this, we have 1 over 12, the square root of u cubed, evaluated from 1 to 9. The square root of 9 cubed minus the square root of 1 cubed times 1 over 12. This is 1 over 12, 27 minus 1, or 26 over 12, or 13 over 6. This is the length of the curve on the interval 0, 1.